Often it is convenient to represent communication signals in the frequency domain rather than using the more familiar time domain representation. The Fourier transform is an important tool for accomplishing this. The Fourier transform is a linear mathematical operation that can be used to represent a signal as a function of frequency, shown here as lowercase omega, which is equal to 2 pi times the frequency in hertz, given a representation of the signal in the time domain. The inverse Fourier transform produces the time domain representation of the signal from the frequency domain representation. Here is an example signal, the sum of two sinusoids of different frequencies and amplitudes, shown in the time domain. In this example, t is a variable and f is a constant. In the frequency domain, each sinusoidal component of the signal appears as a weighted delta function at its respective frequency. The spectrum of the signal, that is, its frequency domain representation, can be written as the sum of the spectra of each of the two sinusoidal components, the first component at frequency f and the second component at frequency 3f. This illustrates that superposition applies in both the time and frequency domains. Therefore, the Fourier transform, the transformation between the two domains, is a linear operation. For clarity, the spectra shown here are single-sided with only positive frequency components. The Fourier transform represents a signal as an integral or infinite weighted sum of an infinite number of sinusoids. If you are familiar with statistics, you can think of the Fourier transform as a cross-correlation of the time domain signal with complex exponentials of all possible frequencies. In general, the cross-correlation function also includes a variable time offset tau between the two functions, but in this case tau is set to 0. For any given frequency f, the function g of f, uppercase g of f, is essentially the correlation of the signal with the sinusoid of frequency f. The inverse Fourier transform reverses this process to return the time domain signal if given the frequency domain signal. In addition to simply undoing the Fourier transform, the inverse Fourier transform can be used to synthesize time domain signals that have desired characteristics in the frequency domain. Here are some selected examples of common functions and their Fourier transforms. And here are some additional examples. Note that the spectra for these signals, that is, the Fourier transforms or frequency domain representations of the signals, can have either odd or even symmetry. The Fourier transform has several interesting and useful properties. Some of these properties are shown here.